Brace yourselves a bit. Server programming isn't as exciting as client-side code. It includes lots of boilerplate code and some complex concepts. Please bear with me. Facebook backend server logic is remarkably complex. What I built took roughly a day of work, maybe a bit longer with debugging. I cut a lot of corners to get this working, especially in the complex data-driven aspects. Some features such as search will be discussed later. This seems like a lot to swallow, but this architecture is remarkably simple once you start looking at it. We have 4 big pieces. Web services. These are thin layers that provide a standard RESTful API. They're encapsulated in the REST controller classes that expose the JSON Web API. Services provide a generic implementation of the underlying logic, so it isn't mixed with web service specific adaptations. Service beans abstract the business logic and JPA from the web service. This means in the future we can port everything to use something like WebSockets and reuse 100% of the code within the service class. DAO, data transfer objects, are used to move data from the storage layer all the way to the client. Spring Boot can translate a DAO object to JSON in a response and create a DAO from JSON. JPA entities. We use JPA to access the database and query/write into it. This includes both the entities and the CRUD repositories. This architecture lets us mix and match pieces as we evolve. I chose to use web services for this app, but tomorrow we could migrate the code to WebSockets and reuse most of the code, as all the pieces from the services layer onwards wouldn't need to change. The same is true for the database. Replacing MySQL should be trivial, as JPA can work with any SQL database. However, you could go even further and replace the entire way data is stored, for instance with a NoSQL database or with direct SQL access. Since the data is hidden from the user, this can be accomplished while leaving major portions of the code intact. To understand how this works, let's review a small sample of the new user creation logic. Request arrives to the server as a web service. It then passes between the layers. Initially, the request comes in as a user DAO object containing the attributes of the user. The response is a new user DAO object that includes additional attributes, specifically the user ID and security token. I'm assuming you have MySQL installed and ready to use. So the next step is the new Spring Boot project. We will need the following features from Spring Boot: JPA, Jersey, security, web services, and MySQL. For completeness, this is the POM XML file dependency section. Notice I'm using Spring Boot 2. We need JPA. Jersey allows us to automatically marshal objects to/from JSON. Security allows us to hash our passwords. We obviously need web services support. We also need the MySQL JDBC plugin. We might as well add 2 additional dependencies. This is a simple REST API which we'll use to communicate with Mailgun to send emails. Twilio allows us to send SMS messages for device activation. Now that all of that is in place, let's proceed to the code. My preferred place to start when working on server code is the database. I might start with the web service if I have an API in mind, but I usually pick the database as it's easier to quantify. But before we go there, we need to add some boilerplate. Assuming you created your app with the initializer, you would have this class. If you don't have it, then you need this class as it's the entry point for your application. Next to it, we can place the security configuration class, which handles basic security boilerplate as such. Here we disable some security protections in Spring Boot. These make sense for browser clients, but not so much for native mobile clients where we might need to jump through hoops to get things working. This is the password encoder that we will use later to hash the user passwords. As I mentioned before, the best place to start a server implementation is the data structure. I will skip the database schema and instead discuss the object entities that we need and how they can serve us. The nice thing about JPA is that it can automatically create the schema for us, which is really useful for fast prototyping. The most obvious object to start with is user. The user class is an entity that handles the data of a person using the app. Facebook obviously holds far more data over each user, but this should be pretty simple to extend. Before I go into the code, there is one concept I'd like to discuss first: unique IDs, also known as primary keys. A very common concept in databases is the usage of an auto-increment unique ID. This means a database would automatically generate a numeric primary key for us, matching every user. This is a really cool but also problematic notion. If our IDs are numeric and sequential, that means we can't really use them outside of the server. If we expose them to the outside world, someone can just scan all our users numerically. A far better approach is a string-based long random ID, which we can generate with the UUID API in Java. The chief value of using this as a primary key is performance. Since queries based on primary key are practically free, it makes a lot of sense to expose the primary key to the client side. Another advantage is database flexibility. It would be possible to migrate to a different database type in the future if we use this approach. An auto-generating strategy can cause a problem as we try to move live data from one database to another. Now that we got that out of the way, let's go to the code. You will notice that the user object in the server is very similar to the user object in the client. There are some differences, but essentially they correlate to one another. We'll start with the field declarations. This is a string ID, as I mentioned before. Notice it lacks the auto-generate annotation you might see in JPA entities. Most of the other fields are simple persistent fields, with the exception of email and phone, where we demand uniqueness from the SQL database. To verify an email or phone, we send out a code and store it here. If we had a memory DB such as Redis or Memcached, we'd use that. But it's not a big deal to use the database for this at first. A user might change his email or phone after the fact, so we need to maintain a reference to the value we verified. Since dates in Java are technically timestamps, we need to explicitly state the SQL data we need here. We store media files such as pictures in a separate media entity. We'll discuss that entity soon. We have three relations to other users for friends, friend requests, and people you may know. The field stores a hashed version of the password, which is encrypted. It's never exposed to the user. Passwords in the database are hashed and salted. This is handled automatically by Spring, as we'll see soon enough. Hashing is a form of encryption that only goes one way. For instance, if my password is XYZ, I can hash it and generate a value that looks completely random. I can't decrypt it ever again. However, if I know the password is XYZ, I can verify it against the hash. Salting means random data is inserted into the hash to make it even harder to break the hash. The token is a special field that allows us to edit a user. We expose it only to the logged in user, and he can use that token to edit the data. We have a unique ID for every user, but we don't use it for write operations. Our ID is public knowledge, so if a user needs to refer to my user object, he'd use my unique ID. This is efficient and accurate since IDs never change. They are primary keys. When a user logs in, we provide the token so only the user can update his own data. This means the password isn't stored on the device, and a token can be updated/revoked. It's also long enough and random enough, which isn't always the case for passwords. Naturally, tokens can't be primary keys, since tokens might need resetting in case of a vulnerability, and primary keys are forever. If I was super concerned about security to a paranoid level, I'd encrypt the tokens in the database in the same way we encrypt passwords. That would mean we would need to give a different token to every device, since hashing is a one-way street. Naturally, that's a pain to handle, so I avoided it here. We initialize the primary key in the constructor. This will be overridden when loading from database, but makes sure we have a unique ID when saving a new user. These methods check the list of friends to see if a person with the given ID or token is in our friend list. We'll use it later. Codename 1 on the client side doesn't support Java 8 streams at this time. They help writing some complex ideas a bit more concisely, but we find them hard to compile to efficient code for iOS. On the server, this isn't a problem. Here we have another case of a stream with a for each method. This is pretty easy to explain with the block above. The stream code is roughly identical to the standard Java for loop. This method handles conversion of lists of users to list of user DAO. This is a common practice as we get a lot of those. We'll use the full name a lot in the code, so it makes sense to have this as a helper method. The birthday can be null, so we need to check before converting to a long value. Here we create a DAO object matching this user. I'll discuss the DAO in more detail soon, but as you recall from before, we use it to transfer data to the client. Notice that no private information is passed when the DAO is created, not even the friend list, no password, token, etc. We pass the auth token here, but not the password. This method is invoked when a user logs in and returns to the user his own data. Looking over the rest of the code, you will notice that the rest is just a lot of boilerplate setters and getters. There is nothing interesting here, but we need this for JPA to function properly. These getters and setters are made through IDE refactorings, so I didn't write them. Before we move to the methods, I'd like to discuss the concept of a DAO. A DAO stands for Data Access Object. This is a conceptual idea. There is no DAO API or requirement. You can skip it entirely. However, it's a very common best practice when working with backend systems. For instance, in our application, we have 3 layers: web services, the user-facing code; services, the backend logic; entities, JPA, the database. The roles are clearly separate. That's important as it means we can replace or change one layer significantly without impacting the others. For instance, we can move to WebSockets, replacing the web services layer, or we can move to NoSQLDB and throw away the entity layer. So how do we transfer data between the layers while keeping them logically separate? Enter the DAO objects. They aren't entities. Entities are too close to the data and are hard to modify. DAOs are in place simply to pass along the data. The cool part about DAOs is that Spring Boot can automatically convert them to JSON when sending a response from the web service, and automatically create a new instance from JSON when receiving a call. We could just pass the entity itself, but that would break the separation of layers and might inadvertently expose private data to the client side. So for the user object, we have a similar user DAO equivalent. The fields are almost identical to the fields of the user object. You will notice that even the relations are DAO objects. Notice that the class includes private data such as password and auth. As you might recall from the user object, we never pass password into the DAO, and it's hashed anyway. So why do we need the password in the DAO? When the user is created or updated, the password value can be set. The DAO is sent from the client side too, and that value may come from there. The token is returned in the DAO once after login or create. The DAO must include a no-arg constructor so it can be instantiated by Spring Boot. We also have a convenience constructor for our use. The rest of the code is all automatically generated getters and setters. The one last missing piece for the user object is the user repository interface, which allows us to query the user objects. The implementation of these queries is generated automatically by Spring Boot based on the names of the JPA fields. Ignore case is a special case keyword for Spring which works exactly as one would think. With that, we have the first entity in the data area and the basic Spring Boot server.